Very good evening, everyone. As you all know, that today's topic of ours is electrochemistry theory, and the part which we will going to cover today is part two. So, let's start the topic NCRT chapter two, electrochemistry theory, part two. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of original creators and owners. If you are the owner and have any concern or issues, please contact us at Sathee at iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using the generative AI, which is experimental. Okay, so let's start with our objective today. So, for today's objective is that after attending this lecture, you will be able to define the standard potential of the cell. Okay, so what are the topics which we will going to cover according to the NCRT in the today's lecture? So, they are: the first one is for the measurement of electrode potential, which comes under the subsection of NCRT textbook in the electrochemistry chapter, and it is marked as 2.2.1. And secondly, the topic which we will going to cover is in text question. So we will see some practice question or in text question which we have taken from the NCRT textbook, which is marked as 2.1, 2.2, and 2.3. So these are the two topics which you are going to see in the today's lecture. Okay, so let's start with the measurement of electrode potential, subsection marked as 2.2.1. In this, let's start with requirement for the standard hydrogen electrode, SHE, it is also known as, right? We will define the standard hydrogen electrode in the later slides. So the potential of individual half cell cannot be measured. Okay, so if you know, previously we have studied about the electrochemical cell, the redox reaction, the half cell reaction, the half reactions of redox reaction, and also we have been seen the representation of a cell, the representation of half cell, and how the half cell reaction has been written. So we have also talked about the potential or EMF of a particular cell. So here it is written that the potential of the individual half cell cannot be measured. So if you are talking about a potential of any half cell, we cannot measure the potential of individual half cell. Only the difference between the two half cells potentials that will give the EMF of the cell can be measured. Okay, so understand what we are saying, that if we have a particular half cell, let's suppose something is reducing and oxidizing at cathode and anode, and we are separating the anions with the salt bridge. Okay, so we have something here, then it is going from this to this, and then salt bridge, and then this, right, this to this. So this is the cell representation we have studied, like let's suppose y to y2 positive, or z to z2 positive, something like this. We have seen the cell representation. So if you are having this, that means this cell can be divided into two half cells. The first one is for y, the second one is for z, right? Now if you want to determine the potential of this one half cell, you cannot do it. You cannot measure the half cell of this individual potential for this half cell, but you can definitely find out the difference between the two half cell potentials. Let's suppose y and x, so these are the two half cells. You can determine their difference in potentials, which will give the EMF of this overall cell. If we arbitrarily choose the potential of one electrode or one half cell, then that of the other can be determined with respect to this. Okay, and now if you get the difference, or if you have the difference for any cell, which is the difference between the two half cells potential for that particular cell, then you can choose the potential of any one electrode, any one half cell, and then you can find out the other respective half cell potential. Okay, so this is what this point is saying. And according to the convention, a half cell, which is called standard hydrogen electrode as SHE, okay, standard S hydrogen H electrode E, represented by this platinum H2 H positive, is assigned a zero potential at all the temperatures corresponding to the reaction. So basically, it is given that according to the convention, we take the potential of the standard hydrogen electrode, and standard hydrogen electrode, also known as She electrode, is represented by this representation, this cell representation, and it has zero potential at all the temperatures. So if you add this SHE, or standard hydrogen electrode half cell, to any cell, okay, as their half part or half cell part, then that this half cell will be having the zero potential. Okay, so you can determine the, you can say, difference between the two half cells, right? Because this one difference potential, this one potential will be zero, the other one you can determine, because you can have the difference between the two half cells if you add, or if you take this half cell of SHE with any cell, okay, which will corresponds to the reaction H positive plus electron. This will give you half of H2 in the gaseous state. Okay, so this is the reaction happening for the standard hydrogen electrode half cell. Okay, platinum here is the catalyst we use, or in this half cell. Okay, so the requirement for the standard, okay, so basically this is standard hydrogen electrode, as the name says, standard. Okay, and if you note anything in which the word standard has been added, or there is a presence of standard thing, that means we are considering the standard states, or standard, you know, state by showing by any element or something. Here we are talking about cell. So standard hydrogen electrode, basically this is a She half cell. So this is basically a half cell first of all. Okay, and the potential you will take for this SHE will be zero. Okay, so the potential you will take, that means E naught you will take for this cell will be 0. For what? For SHE half cell. Okay, now in the further slides, in the later slides, you will see that how we use this SHE electrode with the other half cells to make a complete cell, and how we use this zero potential property of this SHE. Okay, and the reaction which is going on in the SHE is, which is that means the reaction which is associated with the SHE is this one, in which the hydrogen ion is getting or gaining one electron and converting into a hydrogen gas, right? Now let's define standard hydrogen electrode completely, which is, as I said, you can represent by SHE. So the standard hydrogen electrode consists of a platinum electrode which is coated with platinum black. Okay, so in the standard hydrogen electrode, as the name says, it has hydrogen. So hydrogen reaction is going on, but if you see the structure, if you consider the structure of the SHE, it is consisting of a platinum electrode. Okay, in this we have a platinum electrode. As I said, that this SHE is representing a half cell. That means it will be only having one electrode. Okay, and that will also be of platinum. So it will be having a platinum electrode which is coated with the platinum black element. Okay, so it is coated with platinum black. Now the electrode is dipped in the acidic solution and pure hydrogen gas is bubbled through it. In the other type of cells, we have seen that we have a solution in the two beakers, each beaker having electrode of their own, and the beaker is having the solution, or you can say solvent, uh, and these two electrodes are connecting with the wire, through the wire, through which the current will flow externally, and which will cause the functioning of this cell, right? But here we are talking about SHE is a half cell. Okay, this is important, that's why I'm repeating. This is half cell, so we are only using a single electrode which is of platinum, and also it is coating with the platinum black. Now if electrode is there, electrode should be dipped in some kind of solution, so the electrode is dipped in the acidic solution, and what will happen, the reaction happening, and the pure hydrogen gas is bubbling or bubbled through it. The concentration of both the reduced and the oxidized forms of hydrogen is maintained at unity. Now here one thing also you have to remember, that the concentration of the reduced and the oxidized form of the hydrogen, you have to take that at unity, that means 1. Okay, you have to maintain the concentration of the reduced and the oxidized form of hydrogen as 1. This implies that the pressure of hydrogen gas is 1 bar, and the concentration of hydrogen ion in the solution is 1 molar. Okay, as I said that in the SHE the name has standard. Okay, so we take the standard conditions, and we just define this point that the pressure of hydrogen gas you have to take in this is 1 bar, and the concentration of hydrogen ion in the solution will also be 1 molar, as I said this, as I just said in the previous point. Okay, that concentration of reduced and oxidized form of hydrogen is maintained at unity. So okay, one more thing, that why we are talking about hydrogen only, because we are talking about a half cell and only hydrogen is involving in this, because we are getting up our product as hydrogen gas, which is bubbling in this reaction of the standard hydrogen electrode, right? So everything is also considered to be standard, because the pressure should be of 1 bar, and the concentration of the solution should be maintained at unity. You can see this diagram, which is representing the standard hydrogen electrode SHE. This is the figure 2.3, which is also given in our NCERT textbook in the chapter Electrochemistry. So you can see we have a beaker in which a solution is there, which is acidic in nature. Okay, acidic means it is having H positive ions, right? So this you can relate with the acid and base basic definition. So if you talk about H positive, that means we are talking about acid, and if we are talking about OH negative, we are talking about base, right? This is basic definition for the acid and base. Meanwhile, we have different definitions for defining the acid and bases. Okay, but for the basic thing, we are considering that if we are talking about H positive, that means we are talking about an acid, and if we are talking about OH negative hydroxyl ion, that means we are talking about base. Now here the electrode is dipped in the acidic solution, that means it will be having H positive ions inside it. So it is given also that 1 molar of H positive ions is present in this solution. Now we have this finely divided platinum coated on the platinum foil. So we have this electrode of the platinum metal, and it is coated with the platinum black. Here you can see it is written that finely divided platinum, which is coated on the platinum foil. Now we just covered, you can see that we have some covering type of thing on this electrode, and we have also a opening here. So in the solution, the reaction is happening for the hydrogen atoms, and the reduction and the oxidation is happening in a same like half cell, and the hydrogen at the 1 bar you will pass through this opening. Okay, so hydrogen gas at the 1 bar pressure, 1 bar because we are talking about standard hydrogen electrode, you will pass through this hydrogen gas for providing the metal, which is here hydrogen. In the other case it is some metal, but here it is hydrogen. So you are passing the hydrogen gas through this opening, and also it is going inside and making the and doing the reaction. So it is going here through this covering, and here in the solution we have already H positive ions. So H2 plus H2 and H positive ions react with each other, and the bubbles will form, which is of the hydrogen gases. Okay, so this is the overall structure, or this is the overall construction for the standard hydrogen electrode. Now let's talk about the cell potential of the provided half cell. Okay, so how can you define the cell potential of the provided half cell? This topic also comes under the measurement of electrode potential topic, which is the subsection 2.2.1. Now at the 298 Kelvin temperature, the EMF of the cell standard hydrogen electrode second half cell constructed by taking the standard hydrogen electrode as anode, which is reference half cell, and the other half cell as cathode, gives the reduction potential of other half cell. Okay, so this is kind of typical language, but try to understand that at this particular temperature, the EMF of a cell, standard hydrogen electrode, salt bridge, second half cell. Okay, so we are representing this as a cell. This is the cell representation given in the form of words, that we have a standard hydrogen electrode SHE, which we are using here as a half cell, and salt bridge. This is the representation of salt bridge. I also told this in our previous lecture. So this is a representation of salt bridge, which we use to connect two solutions to maintain the neutrality of the solutions, remember. So we are taking the standard hydrogen electrode as one half cell, salt bridge, and the second half cell. So this is given the representation of a cell. So at this temperature, the EMF of this cell, which is given like this, which is constructed by taking standard hydrogen electrode, that means SHE, as anode. Okay, try to understand. Here SHE is taken as one half cell, which is acting as anode. Okay, which is our reference half cell. We will always take this SHE as our reference half cell, as anode in the left hand side of the salt bridge, and the other half cell, that is the second half cell, okay, which we are taking as cathode. So for a given cell at this temperature, the EMF of the cell, which we construct by SHE as anode and second half cell as cathode, will give the reduction potential of other half cell. So if you get the EMF of this cell, it will be the reduction potential of the other half cell. This is what this line is trying to say. Okay, because this standard hydrogen electrode potential will be going to 0, right? So whatever will be the cell EMF, that will be the EMF of this second half cell. Now let's see how. If the concentration of oxidized and the reduced forms of the species in the right hand half cell are unity, then the cell potential is equal to standard electrode potential. Okay, other case is also given, that if the concentration of oxidized and the reduced forms of species which you have taken in the right hand half cell, that means this one, right hand means from the salt bridge it is right hand. So concentration of oxidized and reduced forms of species in this right hand half cell are unity. If you take it as 1, the concentration, then the cell potential will be equal to the standard electrode potential, E naught R of given half cell. Okay, so if you want to find out the E naught of the cell, that means the standard electrode potential, it will be E naught R minus E naught L, right? The standard potential for the right electrode minus the standard electrode potential for the left electrode. This is the formula for determining the E naught of the cell. Okay, in other form it can also be written as E naught of cathode minus E naught of anode. This is the other form you can say. So RL we are using because we are just considering here that this will act as cathode, this will act as anode without any reaction. So that's why we are writing R and L. So E naught of cell is defined as E naught R minus E naught of L. Now, as the E naught of L for standard hydrogen electrode is 0, L representing left hand side, the left hand side from salt bridge. The left hand side from salt bridge is standard hydrogen electrode, whose potential we just have discussed that will be equal to 0, right? That means its standard hydrogen electrode, the standard hydrogen electrode will be having the E naught L value as 0, right? So we put this equals to 0 here. So E naught of cell will become equals to E naught of R minus 0. That means E naught of R, right? So the given half cell and the overall standard electrode potential of the cell will become equal, right? Because we are using the reference half cell as standard hydrogen electron, right? So that's the main reason, and this is the thing that which our first point is explaining us. Now, illustration of calculation of EMF of the cell. Now, if you want to find out the all illustration that how you can calculate the EMF of the cell. So, let's suppose we have this cell. Okay, this in this you can see that this is the salt bridge. So, this one is the right half cell. This one is the left half cell. This is clear. Now, you can also observe that the left half cell is similar to the SHE, or it is SHE basically. Okay, platinum H2 in the gaseous state and at 1 bar pressure, and H positive in the aqueous state and 1 molar or unity concentration. Okay, so this left half cell is basically standard hydrogen electrode half cell. Now, here in the right half cell we have copper half cell, which is Cu2 plus in the aqueous state and at 1 molar concentration, and it is converting to the copper. Okay, so this is the cell representation, the overall. Okay, don't remember, this is the overall cell representation, as it is containing the anode cell reaction and the cathode cell reaction both. Now, the measured EMF of this cell is 0.34 volt. For this cell, the measured EMF is 0.34 volt, and it is also the value for the standard electrode potential of half cell, which is corresponding to the reaction, which is given as Cu2 plus in the aqueous state and 1 molar concentration plus 2 electrons, giving us the copper in the solid state. Okay, so first of all, what we said that how we are going to illustrate how you can calculate the EMF of the cell using the SHE. Now we have given a cell representation, which is this one, in which the left half cell we are using is SHE and the right half cell we are using is the for the copper, right? So the measured EMF for this given cell is 0.34 volt, which is positive, and it is also the value for the standard electrode potential of half cell, which is corresponding to the reaction copper 2 plus 2 electrons, giving us copper, because the copper half cell is our right half cell, right, in our cell representation. That means the overall cell electrode potential will be equals to the electrode potential or standard electrode potential of right half cell, which is corresponding to this reaction. This is the reaction for the copper reducing, right? Copper is gaining the electrons and converting to copper 0 in the neutral state. So 2 positive to 0, that means it is reducing. Now, let's suppose we have this another cell in which again we are using the platinum and this SHE, right? And the right half cell is for zinc. Okay, zinc 2 positive and zinc. If you see, we have in the gaseous state, H2 is in the gaseous state at 1 bar pressure, H positive in the aqueous state and 1 molar concentration, while zinc 2 positive is in the aqueous state and 1 molar concentration. So this is at the left hand side we are using SHE, and the right half cell we are using for is zinc. Now, similarly, the measured EMF of this cell given is minus 0.76 volt. Now, you can observe that when you have taken the copper case, this value of the EMF is positive, and when you are taking zinc as the right half cell, the measured EMF values become negative. So this is corresponding to the standard electrode potential of half cell reaction, zinc 2 plus 2 electron giving us zinc. Okay, this is same we discussed in the previous slide, that zinc 2 positive is reducing here by gaining the 2 electrons and going from 2 positive to the 0, that means the neutral state. Okay, so whatever the standard electrode potential or the EMF of the overall cell is coming, that will be equal to the standard electrode potential of the half cell, which is present at the right hand side, right? Now, the oxidation and the reduction on the basis of positive and negative value of standard electrode potential. So as you just observe that we have at once the positive value of E naught, and at another time we have negative value of standard electrode potential, when only we just have changed the half cells of present at the right hand side. So the positive value of standard electrode potential in the first case, where 0.34 volt is the value of EMF when copper 2 positive is reducing. Okay, so this will indicates that the copper 2 positive ions is getting reduced more easily than the H positive ions. Okay, so the summary is that the copper 2 positive ions get reduced more easily than the H positive ions. Why we are saying that? Because the overall EMF coming for the cell is positive 0.34, and this will be equal to the E naught for the copper cell, copper 2 positive to copper cell, right? This is the E naught. This is same the E naught of the right half cell, because the left half cell is SHE. Okay, now the E naught for the copper cell, which is corresponding to the reducing reaction of the copper. So the EMF value or the standard electrode potential value is coming out as positive. Now what does that indicate? This indicates this statement that the copper 2 plus ions get reduced more easily than the H positive ions. Okay, why H positive ions we are saying? Because the other half cell we used is SHE, that is standard hydrogen electrode, where the hydrogen reaction is happening, right? So that's why we are comparing the copper and the H positive ions. The reverse process cannot occur, that is, the hydrogen ions cannot oxidize copper. Reverse reaction means SH positive and copper 2 positive. Okay, so H positive reduce, copper 2 positive. So hydrogen ions cannot oxidize the copper, or alternatively you can also say that hydrogen gas can reduce the copper ion under the standard conditions. Okay, so this is the reverse process which we are saying cannot occur. Thus, copper does not dissolve in the HCl. Now you can also use it for this reason, that copper element does not dissolve in the HCl, hydrochloric acid. In the nitric acid, it is oxidized by the nitrate ion and not by the hydrogen ion. It can dissolve in the nitric acid because it is oxidized by the nitrate ion and not by the hydrogen ion in the case of HCl. That's why it does not dissolve in HCl but can in the nitric acid. The negative value of standard electrode potential in the second case, okay, now in the second case when we use zinc as the right half cell, then the EMF value is minus 0.76 volt when we use zinc 2 positive. Zinc 2 positive is reducing. So the negative value of minus 0.76 volt for the right half cell, indicating that hydrogen ions can oxidize zinc. Or you can say that zinc can reduce hydrogen ions. Alternative. Okay. If hydrogen can oxidize zinc, that means zinc can reduce hydrogen. Right? Simple. Now, let's see the determination of EMF for the Daniell cell. So, the half reaction for the Daniell cell in the figure 2.1 can be written as, now if you see, this is the figure 2.1, which is a Daniell cell having electrodes of zinc and copper dipping in the solutions of their respective salts. Here we have zinc sulfate, here we have copper sulfate solution. We have zinc rod in the zinc sulfur solution. We have copper rod in the copper sulfur solution. And the two rods are connecting through the external circuit through which the current is flowing from the copper to the zinc, and the electrode is flowing from the zinc to the copper, right? And this is the salt bridge. So the half cell reaction for the Daniell cell, if you want to write out, it will be at the left electrode, that means the zinc electrode, the reaction happening is this, which is zinc converting to zinc 2 plus plus 2 electrons. That means it is releasing the electrons in its solution. And similarly at the right electrode, the reaction happening is the gaining of the electron. That means copper 2 plus is gaining the electrons and converting the neutral copper, right, from 2 positive to the neutral copper. Here in the zinc case, from the neutral to the zinc 2 positive. Okay, so oxidation is happening at the left electrode and the reduction is happening at the right electrode, which is of copper and it is of zinc. Now the overall cell reaction of the cell is the sum of above two reactions and we obtain the equation. Okay, we just see the two half cell reactions. So if you want to see the overall cell reaction, it will be the sum of the two reactions, two half cell reactions. So we just add the two half reactions. That means we add the left electrode reaction and the right electrode reaction together. The electron are equal in both the electrodes, so it will cancel out, and the reactant side will add up together and the product side will add up together, and the overall cell reaction will become zinc plus copper 2 plus, giving us zinc 2 plus plus copper. So this is the redox reaction for the overall cell, where the zinc is undergoing the oxidation process and the copper is undergoing the reduction process simultaneously. The EMF of the cell, if you determine, it will be E naught of cell equals to E naught of R minus E naught of L. R is representing the right and left, L is representing the left. So it will be 0.34 volt for the right hand side, that means for the zinc one. Okay, so for the zinc electrode, the electrode for the zinc, you can say zinc reduction, is 0.34 volt, and the left hand side electrode potential will be minus 0.76 volt. And you just simply write this value in the brackets because already negative is present outside of the bracket, and this will get multiplied, minus minus will become plus, and when you add these two quantities it will be equal to 1.10 volt. So this overall cell reaction will be having the EMF equals to 1.10 volt. So this is how you can obtain the EMF for the Daniell cell, in which if you know the left and the right electrode and the processes happening or the reaction happening at each of the electrode, you can determine the EMF by just subtracting the E naught of R, that means right electrode, minus the E naught of left electrode. Now let's see the examples of inert electrodes. The metals like platinum or the gold, which are used as inert electrodes. Okay, so platinum or gold are used as inert electrodes because they cannot they will not react as much, or you can say they do not have this much of reactivity to react with anyone. So platinum and gold, they are generally used as inert electrodes. They do not participate in the reaction, they do not react, but provide their surface for the oxidation or reduction reactions and for the conduction of electrons. Okay, that's why we are calling it as inert electrodes, and why we are using it, because they do not participate in the reaction and they provide the surface for the happening of oxidation and reduction reactions and for the conduction of the electrons, the passage of the electrons. For example, platinum is used in the following half cells. So hydrogen electrode, this is a hydrogen electrode where the platinum we use and the H2 in the gaseous state and H positive in the aqueous form. Okay, this is a hydrogen electrode. This is with half cell reaction where H positive plus electron is giving us half of H2. So this hydrogen electrode is associated with this half cell reaction, which is H positive gaining an electron and becoming the hydrogen gas. The bromine electrode where we use the platinum, like platinum Br2 in the aqueous form and Br negative in the aqueous form. This is a bromine electrode where we are using the platinum surface or the platinum rod. This electrode is associated with this half cell reaction, which is half of Br2 gaining an electron and becoming negative Br negative ion. Okay, so these are the examples in which the platinum is used in the half cells. Now let's see the electrochemical series. So this is a table which is marked as table 2.1 of standard electrode potentials at 298 Kelvin temperature. Okay, so ions are present as aqueous species and water as liquid. Gases and solids are shown by G and S. Okay, so ions are in aqueous state, water is in liquid, and the gas and solid are represented by G and S symbol in this electrochemical series. So this is a whole series in which we arrange different ions or the molecule or the elements in the ionic form uh, according to their E naught value in the volt. Okay, so this is the whole, you can see this is the decreasing order for the E naught value. 2.87 is the highest for fluorine and minus 3.05 is the lowest for the lithium positive ion. Okay, so this is a whole series given and arranged by the decreasing order of the E naught value for different ions or the molecules. And these are the reactions. So this is the reaction in which we take the oxidized form of the element plus the number of electrons it is gaining, and here in this row or in this column we have reduced form of the oxidized ion we have taken. Okay, so this is a whole reaction. You can see it is written increasing strength of oxidizing agent in this order. Arrow is on this side, and this is the increasing strength of reducing agent. Arrow is on this side. Okay, here 2 points are mentioned. First, a negative E naught means that the redox couple is a stronger reducing agent than H positive or H2 couple. And secondly, a positive E naught, you can see that we have positive and negative E naught, but we have here 0 E naught value, which is for the H positive H2 couple. Okay, so we are saying if the E naught value is negative, that means that redox couple will be the stronger reducing agent than the H positive H2 couple, right? But if we are having a negative, if we are having a positive E naught value, that means that redox couple is a weaker reducing agent than this H positive H2 couple. Okay, so we are comparing with this couple because the E naught value for this is considered as 0. Now, significance of the electrochemical series. If the standard electrode potential of an electrode is greater than the 0, then its reduced form is more stable compared to the hydrogen gas. Okay, so if you have an electrode and the standard electrode potential of that electrode is greater than 0, then its reduced form will be more stable compared to the hydrogen gas. Similarly, the opposite way, that if the standard potential is negative, then hydrogen gas is more stable than the reduced form of species. Now, it can be seen that the standard electrode potential for the fluorine F2 is the highest in the table of electrochemical series, right? We saw that fluorine is on the top because its E naught value is the most positive value, indicating that fluorine gas has maximum tendency to get reduced to the fluoride ions F negative. Okay, and therefore the fluorine gas is strongest oxidizing agent because it can oxidize the and get reduced itself, and the fluoride ion is the weakest reducing agent. Okay, weakest reducing agent means it can weakly reduce others and get oxidized itself. Okay, so this is the explanation which we give after seeing the electrochemical series. Now, lithium has lowest electrode potentials. On the other hand, if fluorine have the highest electrode potential, lithium is at the bottom of electrochemical series, which is having the lowest electrode potential, which indicate that lithium ion is weakest oxidizing agent. Okay, that means it can weakly oxidize those and get reduced itself, while the lithium metal is most powerful reducing agent in an aqueous solution. It may be seen that as we go from the top to the bottom in the electrochemical series, which marked as table 2.1 in our NCERT textbook, the standard electrode potential decreases, and with this decrease the oxidizing power of species on the left and the increase the reducing power of species on the right hand side of the reaction. Okay, if you consider, or if you observe the table, we have reaction given where there is an oxidized form. Okay, let me write. We have the oxidized form, or you can say oxidized ion, and the number of electron which it is gaining, and then the reduced form, or you can say reduced ion, right? So what we are saying, that if you go from top to bottom in the electrochemical series, standard electrode potential, that means the E naught value which just given in the last column, the the standard potential decreases, right? It is decreasing in this manner, right? Highest is here for the fluorine and the lowest is here for the lithium ion. So the electrode potential is decreasing, and with this decreasing value of electrode potential, the oxidizing power of species on the left, that means this one, oxidizing power of species on the left is also decreasing, and increase the reducing power of species on the right. Now, right from the arrow, reaction arrow. So reduced ion, reducing power is increasing. Okay, this oxidized ion, oxidizing power, oxidizing power is decreasing as the E naught value is decreasing, and the reduced ion reducing power is increasing as the E naught value is decreasing. This is what this line is saying on the right hand side of the reaction. Okay, this is the reaction. If you observe the table, you can again see the table and present in your NCERT textbook and marked as table 2.1. Okay, so oxidizing with the decrease of E naught value, oxidizing power of oxidized ion is decreasing, and reducing power of reduced ion is increasing. Electrochemical cells are extensively used for determining the pH of the solutions, solubility product, equilibrium constant, and other thermodynamic properties, and for the potentiometric titrations. So these are the some uses where you can use the electrochemical cells with the help of electrochemical series. Okay, now let's see some in-text question. So let's see the first in-text question, which is marked as 2.1. The question asks that how would you determine the standard electrode potential of the system Mg2 positive to Mg. So this system is representing a half cell. This should also have a half cell reaction. How can you determine the standard electrode potential of the system? This is the question. Okay. So we solve this question using the NCERT subsection 2.2.1. And before that, you have some time, you can go through it, try to solve it, analyze it, and then we can see the correct answer. Okay, so let's see. So for this question, how you determine the standard electrode potential? Let's see. So the standard electrode potential of this Mg2 positive to Mg system can be measured with respect to standard hydrogen electrode. Okay. So one thing to remember here, if you have given a system which is only representing one half cell, but for a cell, for a complete cell, you need the both half cells which present at left hand side and right hand side of the salt bridge, right? Now we have only provided one half cell, so you will just take the other half cell, or you take the other half cell as reference as standard hydrogen electrode. Okay, because it will be easy, because you know the potential for this, which will be 0. So the for determining the standard electrode potential of this half cell or the system Mg2 positive to Mg, the standard electrode potential can be measured with respect to standard hydrogen electrode SHE, represented by platinum H2, which is present at 1 atmosphere and in the gaseous state, to H positive in the aqueous form and 1 molar concentration. This is nothing but just given the representation of SHE. Now, a cell which is consisting of MgSO4 in the aqueous form, 1 molar concentration as the anode, and the standard hydrogen electrode as the cathode, SHE as the cathode, is set up. Okay, now we have set up the cell where we are using the anode as this system, which is already mentioned in our question, as anode, and we are using the SHE as the cathode. So representation first of all. So if you represent this, it will be Mg2 plus, salt bridge H positive H2 platinum. Okay. So this cell and this SHE cell, and this is salt bridge, differentiating the two half cells. Then the EMF of the cell is measured, and this measured EMF is standard electrode potential of magnesium electrode. This should be clear up by now. Right, this should be clear by now to you, to all of you, because we have studied this definition so many times in this lecture that if you are using SHE as one half cell, when you determine the overall electrode potential of the cell, that will be equal to the standard electrode potential of another half cell other than the SHE. Okay, so this is the thing only. This is written in this point, that EMF of cell is measured of cell. Okay, EMF of cell, overall cell, is measured, and this measured EMF will be standard electrode potential of magnesium electrode. So E naught, you know, how can you determine for a cell? It will be E naught of R minus E naught of L. Here the E naught of R for the standard hydrogen electrode is 0, because at the right hand side of salt bridge we take the SHE. So E naught of R will be 0. We simply put it in this equation, and therefore the E naught will become 0 minus E naught of L. That means minus of E naught of L. So the total overall cell electrode potential is equals to the minus of the standard electrode potential of the left hand side, which is this Mg electrode. So this is how, and if you know the value, you can put it simply here and you can determine the standard electrode potential of the system Mg2 positive to Mg. Okay, so this is the way you can solve this for determining the E naught of the system given in the question. Okay. So this is our next in-text question, which is 2.2, which is marked as 2.2 in our NCERT textbook. The question says that, can you store copper sulfate solution in a zinc pot? We have given the standard electrode potentials for zinc as minus 0.76 volt and for copper as 0.34 volt. So you can use the NCERT subsection 2.2.1, which we covered in this lecture, to solve this question. Analyze this question, and then we will see what will be the correct answer. How can you explain it? Okay. So when you answer this question, first of all, it is telling, or it is asking you that, can you store the copper sulfate solution in a zinc pot? So that means it is needing to answer this question. It is need to answer this question in a yes or no format, right? But also the E naught value is given. The E naught value is given. That means you have to just explain a little bit. So the zinc whose E naught value, the standard electrode value, is given as minus 0.76. Remember, here it is negative. So zinc is more reactive than the copper. Copper is having 0.34 volt in the positive. So zinc is more reactive than the copper. You can clearly see, or you can clearly relate it by their E naught values. Therefore, zinc can displace the copper from its salt solution. Okay, so if you have a solution of a copper, or you can say we have a salt solution of copper, if you add the zinc, zinc can displace the copper from that solution. So if the copper sulfate solution we have, and when you store it in a zinc pot, the zinc will displace the copper from the copper sulfate solution, and the following reaction will takes place. The zinc will react with the copper sulfate solution and displace the copper. So zinc sulfate plus copper we will get. Hence, we cannot store, or we cannot store this copper sulfate solution in a zinc pot, because zinc is more reactive than the copper. And we determine this by seeing their E naught values. The zinc value is negative. That means if you relate it to the electrochemical series, the E naught value negative is at the bottom side. Okay, and the E naught value is positive for the copper, which is at the top side. So by this you can conclude that zinc is more reactive than the copper. That means zinc has the tendency to displace, or to displace the copper in its own solution. Okay, that's why we cannot store copper sulfate solution in a zinc pot, because following reaction will takes place. Okay, now this is our next question, which is marked as 2.3. Consult the table of standard electrode potentials and suggest 3 substances that can oxidize the ferrous ions under the suitable conditions. This is a table in which we have given a reaction in which we are taking the oxidized form plus n number of electrons, and then the reduced form, and their respective E naught values in the volt. First is for the Fe3 plus gaining an electron becoming Fe2 plus. The E naught for this process or this reaction is 0.77. Cl2 gaining 2 electrons becoming 2Cl minus. The E naught is 1.36. And O2 is gaining 2H positive. O2 is combining with 2H positive and gaining 2 electrons becoming hydrogen peroxide H2O2. And the E naught for this is 0.68. You can solve this using the NCERT subsection 2.2.1. Your time starts now. So, how can you solve this reaction? How can you solve this question? So, what we are asking that suggest 3 substances that can oxidize the ferrous ion under the suitable condition after consulting this table. So, the substance that are stronger oxidizing agent than the ferrous ions can oxidize the ferrous ions, right? So, Fe2 plus will give us Fe3 plus electron. This is the oxidation reaction for the Fe2 plus. We just write the reverse reaction for this given first reaction in this table, right? So its E naught value will get reverse. So positive will become negative. This implies that the substance having higher reduction potential than positive 0.77 volt can oxidize the ferrous ions to the ferric ions, and which can accept the electron which is released during the oxidation, or are placed above the iron in the electrochemical series. So the elements or the ions who is having the E naught value greater than the 0.77 volt, which is for this ferrous ion, can oxidize the ferrous ion to ferric ion, or you can consider this, or you can determine those ions by looking this table and also by looking in the electrochemical series. Whatever the elements in these, from these 3 ions, whatever the ions are having or are placing above the iron in the electrochemical series, that will be our answer. Okay, so 3 substances that can do so are F2, first of all, whose E naught value is 2.87 and it is above the ferrous ion. Second is Cl2, whose E naught value is 1.36, and third is O2, whose E naught value is 1.23. All are having the greater reduction potentials than positive 0.77 volt, which is for ferrous ion as given in this table. Okay, so this is how you can tell the number of or the three substances that can oxidize ferrous ions by consulting this given table where the three reactions are given and their respective E naught values are given. Okay. Okay. Thank you very much for joining this session. This is all for today's chemistry session.